Hello. In this video, we're going to look at multivariable functions. What do we mean by multivariable functions? We mean functions with multiple independent variables. All right, so let's just jump right in. So the first case we're going to look at are two independent variables. All right, so a function with two independent variables takes an input x comma y, both of which are independent variables that are in the domain, and produces an output z equal to f of x comma y in range R. So I'll comment more on some of the specifics in this definition in a minute. What I'm going to do is go through a second definition, which is we not only typically look at functions with two independent variables, we also look at functions with three. So let's just write that out as well. The definition is basically the same, except we go through and have three independent variables. So a couple comments. So these two definitions are effectively the same definition as we have with traditional functions, functions that have a single independent variable, right? So if you just kind of were to compare these, right, if you were to recall, we have x is the independent variable, and we go through and have y equals f of x as our, is our traditional function, where y is the output. And so if you were to translate this for our these two definitions for our traditional function structure, it would just say a function with one independent variable takes an input x in domain D and produces an output y equals f of x in range R, right? It would look exactly like this, except we would just have a single x here and we'd have y equals f of x here. And so it's the same definition. We haven't changed the definition. It's just we're just having two inputs, two independent variables, and one dependent variable, as opposed to one and one, which is what we have done traditionally, right? Another comment is that as functions become more complicated, typically you might see the definition, instead of using input output, they might use mapping, right? So you might see a definition that says, a function with two independent variables, maps xy to z equals f of xy. So a mapping versus input output, those are the same idea. So there's really no difference between those. It's just the way of viewing it. Okay. On top of that, the other thing that I wanted to get into here is the definitions for domain and range, right? So we got domain, range. So those definitions are still the traditional definitions. So domain is still going to be the set of all possible, the set of all, yeah, the set of inputs that produce a finite output. Okay, of course, the difference here is the set of inputs is going to have two components to it instead of one component. So instead of having a domain where we just have x, now we're going to have the domain and it's going to have x and y, all the possible x's and y's. And then the range is still the same definition for range as we have traditionally. That's the set of all possible outputs. Finite outputs. So those are kind of our introduction to get us started. And so just recap one more time. So we're just taking our traditional definition, x and y, right? Input x, output y. X is the independent, y is the dependent, and we're just extending it by adding a second input, a second independent variable, and then instead of having y as the output, if you have x and y as the input, then you're going to make z the output. And then it's also possible to have x, y, and z as inputs, and then we use w as the output instead. Okay, and so that allows us to extend our natural definition for a function to have two inputs and three inputs. All right, so let's go ahead and play around with that for just a bit, just to see what the effects of that are. So if we have f of x, y, so this is our function definition. Let's say it's 2x plus sine y, right? So how do we go through and plug things in? Well, traditionally, you just put numbers in place of the x and the y, or expressions. You can also plug expressions in, but typically when you're first starting, you plug in numbers in. So typically you just go through and put numbers in place of x, right? So if we're going to go through and plug in stuff into this, we're going to put numbers in place of x and y. All right, so if you do f of, we could plug in 1 and we could plug in 0. And traditionally with functions, whatever you put in place of x and y on the left, you put in place of x and y on the right. So we're going to just do that as well. So we have 2 times 1 plus sine 0, and that's going to equal 2. So long story short, the way that you plug in, the way that you go through and use functions is the same as the way that you've used functions traditionally. Normally we plug in numbers in place of x, and then whatever you do on whatever number you put in place of x on the left, you put in place of x on the right. You're just doing the same thing with both x and y instead of with just x. So it works the way that you would expect that it would work, right? If you just guessed, if someone wrote this and said, what do you think f of 1, 0 would be? If you just guessed this, your guess is the right guess. It works the way that you would anticipate. Okay, so if we plug in -3 and pi over 2, you can see I've put a -3 where the x is, I put a pi over 2 where the y is, so we're going to do the same thing on the other side of the equal sign here. So we're going to have 2 times -3 plus sine of pi over 2, which would equal -6 plus 1, which is -5. Okay, and so there's an example of function, and we plug some stuff into it. That's how it works. Let's try another one. So what if we had, how about cosine of xy? And then we can go through and plug in some stuff. We could try plugging in 1 and pi over 4. If we did that, we would get cosine of 1 times pi over 4. That would be cosine of pi over 4, which is root 2 over 2. And again, what I did there is I just, since on the left side here, if you just line this up, I put a 1 where the x is, I put a pi over 4 where the y is. And so I'm just replacing all the x's with 1s, and I'm replacing all the y's with pi over 4s. If we wanted to go through and plug in pi over 6 and 2, you could do that. So we get cosine pi over 6 times 2 is cosine pi over 3, right, which would give us 1/2. Okay, so there's a couple examples for how to go through and use a function with two independent variables. Let's try one with three, just real quick, just to, you know, I think you can figure it out, but you can see that it also works pretty much as you'd anticipate. So let's say we had x, y, z squared. You could go through and plug in 1, 2, 3. If you plug in 1, 2, 3, you put a 1 where the x is, a 2 where the y is, and a 3 where the z is. So just replace those on the right-hand side with their corresponding value. So we're going to put a 1 where the x is, a 2 where the y is, and a 3 where the z is. And you'll end up with 18. All right. We could go through and we can plug in other stuff. You could plug in weird stuff. You could plug in pi. You could plug in e. You could plug in root 2. So you could plug in some irrationals. And what happens? Well, you put a pi where the x is, an e where the y is, and a root 2 where the z is. So we're just going to do the same thing on the other side. So we're going to get pi times e times root 2 squared. And so that would be 2 pi e. Okay. And so that's how that's how the functions work. That's how functions of several independent variables work. They work exactly the same way as functions with a single independent variable. All right, how about domains? Let's go through and try finding some domains. All right, so let's say we start with f of x, y equals 1 over 4 minus x squared minus y squared. All right, and we want to go through and find that. So we want to find the domain. So we want to find everything that we can plug in that will produce a finite output. All right, well, so to go through and do these domain problems, what you need to do is you need to recall how to find a domain with a single variable, right? So if we were just to kind of compare this, if you're asked to find a domain, if I said find the domain for f of x equals 1 over 4 minus x squared, right? So you only had one independent variable, just a traditional function. So the way that you do that is you think about what causes a problem with fractions, and that would be having a 0 in the denominator, right? If we have a 0 in the denominator, that's undefined. That is not a finite output, and so that's the way that you go through and think about finding domains. You think about what characteristic does the function have that we can use to go through and find the domain? And the characteristic that fractions have is that we can't have a 0 in the denominator. And so the way that you go through and do this is you say, well, 4 minus x squared cannot be 0, right? And then from there, you could go through and move stuff around, and you'll end up getting that x cannot be 2 or negative 2. Okay. And so we would say the domain is x such that x is not equal to 2 or negative 2. Right? That's how you'd go through and do it with a single variable, right? So we need to start there. So you need to understand that process before you could try and do the process with multiple variables. All right, so how does this problem play out differently then? Well, it doesn't really, not much. The second variable is going to create some issues, but you start off with the same way. You've got a fraction here. You're like, all right, well, 0 in the denominator is not okay. So we're going to say that 4 minus x squared minus y squared cannot be 0. And then you can move some things around, and you'd say x squared plus y squared cannot equal 4. And now at this point, you can't go through and solve for the 2 because there's a lot of different possibilities here, right? So you could have x be 2 and y be 0. You could have, square root 2 and square root 2 for both x and y. There's a lot of possibilities. And so because there's a lot of possibilities, we actually can't go any further to solving the problem like we did with a single variable. And so we really just stop there and we say, well, what's the domain? It's going to be the set of x and y's such that x squared plus y squared is not equal to 4. And then the difference between the second difference, right, is that that second variable, because we have that second variable, rather than just stop here, which is what you would have done back in an algebra class, we go through and sketch the domain. Because there's a lot of different possibilities, the way that we can look at them is we could visualize the pattern of those possibilities to try and be able to try and interpret what the domain is. And so how do you go through and graph? How do you go through and graph that? Well, we will see just a second. So we need to have a coordinate axis. And then anytime you're going through and graphing a something that's not equal, you can or an inequality, you start off by graphing equality, right? So if we had x squared plus y squared equals 4, we would know what that looks like. So we're just going to start there with equal to 4. And then instead, because it's not equal, right? So what we're going to do is, instead of drawing a solid line, and I'll explain this in a minute, I'm going to draw a dashed line for the circle, right? So we're going to draw a dashed line. Okay. Now, so that dashed line, that represents the places where x and y are not equal to 4, right? The x squared plus y squared is not equal to 4. The locations that create a problem, that create that 0 in the denominator. And so if it's not on that dashed line, then it's totally fine, right? So it's totally fine. So the way that you graph things that are totally fine, the way that you graph things that are true, is you typically shade them. So you can, maybe, I don't know if I can do this with the writing tablet, but you could try it. So you can just kind of shade. Yep. That's where it's true. Here it's true. Here it's in the domain. This is in the domain. In the domain, it's the dashed line where it's not in the domain, right? So the shaded represents being in the domain. In the domain. And the dashed line is not. Okay. And so you can just follow that pattern when you go through and do these problems. You want to shade what's in the domain and use a dash line for something that's not. If you had to draw a line and that line represented things being in the domain, which we'll do one like that in a moment, then you use a solid line. So dashed line, not in the domain, solid line is in the domain. So it's kind of like the equivalent of open circle and closed circle when it comes to a single number line. And so that's the way that we handle the equivalent of those, is that the dashed line is the equivalent of the open circle, and the solid line is the equivalent of the closed circle. All right, let's do another one. All right, so we have f of xy equals the square root of 2 minus x plus y, right? And so what are the characteristics of a square root function? So I'm not going to go back and do one, from a single variable. That's, you have to go back and do some review if you don't remember how to do those. But the way that the characteristic that matters about this, for a square root, is that the values under the root have to be greater than 0 or positive, right? If they're negative, then that's a complex number, and we're dealing with real numbers in this class. And so, complex numbers are not going to be in the domain. And so we could go through and just say 2 minus x plus y. That's what's underneath the root. The stuff that's underneath the root has to be greater than 0 or equal to 0. So that's the characteristic of roots that you use for going through and finding domains for root functions. What you can do is you could go through and, or at least what I'm going to do is I'm going to get y by itself. And I'll show you y in a second. But that's not necessary, but you could go through and get y by itself. But there really isn't anything more that we can do other than maybe getting y by itself to solve for, what the structure would be for the domain. Instead, what you want to just say is that at this point, that xy has to be, we have to have 2 minus x plus y has to be greater than or equal to 0. or you could put this instead. Either way, you want to go through and explain what is going to be in the domain, and you're not going to be able to solve for specific x and y values, and because of that, you're going to end up with something that's an inequality. This inequality is not any more legitimate than that one. However, this one is more useful for graphing, and that's why I went ahead and solved for y. All right, so let's go through and sketch the solution. So the way that you can sketch it, you could draw a number line, draw a coordinate axis. And then once you draw the coordinate axis, we've got our inequality here. So you can start off by graphing equality, just like we did on the last one. So we want to graph where y equals x minus 2. And of course, that's quite simple for us to do, right? That's going to have a y-intercept of -2 and a +1 slope. So we end up with the line that goes through those 2 points. Let's see if I can draw this. Pretty close. All right. Now you notice I'm drawing a solid line. I'm not drawing a dashed line. Why am I drawing a solid line? Because of the equal to, right? So that's going to be included in the set. So the line itself, the points that are on the line itself, are going to be in the domain. They are going to satisfy this equation, and this equation is stuff that's in the domain. So it's important that you recognize, the difference between finding the domain for different problems. So in this problem, when we have a fraction, we're trying to find things that would cause the denominator to be 0, and then we're saying that they can't be those things. So it's just, that's the way that you handle fractions, is you take the denominator and you say it's not equal to that. And then the way that you handle roots is you take what's underneath the root and you say what it can be greater than or equal to 0. So they're kind of opposites in that way, but you have to be able to adjust. And then, so what do we do from there? All right, so once you've got where you have equality, you want to go through and you can use the inequality. If you're not sure, you can use test points to figure out where to shade. So you could take 0, 0 and plug that in. Is 0 greater than or equal to 0 minus 2? Yes, it is. And so this side of the line that we graph should be shaded, right? So you just want to go through and see. This is like so awkward. You just want to shade over here. That came out okay. And then this area that's not shaded, this would be the stuff that's not in the domain. And then this area that's shaded is in the domain. And the solid line also represents being in the domain. So that would be the sketch. So that's how you find the domain with square roots. You want to take what's under the domain. It has to be greater than or equal to 0. And then you can go through and just state that. And then to go through and graph it, each problem may be subtly different, but in this case, we could easily get y by itself and put it into an mx plus b form, which allowed us to go through and graph the line. Okay, and so that's the domain and the picture of the domain for that one. All right, let's do one more. Let's say that we want to go through, let's do a new page. We want to go through and find and sketch the domain. And this time we have 3 independent variables. Okay, so how does that change things? It doesn't change things until we get to the sketch part, right? So what you need to start off with is recalling, how do you find the domain for natural log functions? What's the characteristic of a natural log function that enables us to go through and find the domain? And if you recall back to a single independent variable that we had in a natural log function, the characteristic is that natural logs are only defined for values that are greater than 0, right? So inputs that are greater than 0. So the input has to be greater than 0. So no equal to. Essentially, natural logs are like roots, except you don't have the equal to. So we start off and we say 4 minus x squared minus y squared minus z squared has to be greater than 0, right? No equality. Natural log, you can't plug a 0 into a natural log. And then at that point, if you wanted to, you could go through and maybe move these negative terms to the other side to get 4 is greater than x squared plus y squared plus z squared. But there really isn't anything further that you can do to go through and find specific points, because there's a lot of points that satisfy this. So once you get there, you just want to go through and say that the domain, and now the domain for a 3-input function is going to have 3 inputs. The restriction on that domain is that you have 4 is greater than x squared plus y squared plus z squared. Okay, and so that's going to be the domain. And then as far as sketching, so if we wanted to sketch this, so if you're sketching the domain, you're just sketching this inequality here, right? And so how do we go through and sketch inequalities? Well, you want to start off by graphing where they're equal to. And then once you've got graphed where they're equal to, you can then go through and use a test point to figure out which side to shade. All right, so let's just do that. So we'll do over here. Oh, hold on. That was not going to work anyway, actually. Yeah, let's do it right here. I think there's enough space. Oops, something went wrong there. I can't seem to erase it. All right. There we go. Just ignore that little arrow that's sitting there at the origin. Okay, so how do you go through and graph? So what would equality be for this? It would be where 4 equals x squared plus y squared plus z squared, and we have graphed that before. So if you recognize that, that's a sphere, and you can go through and you can use cross sections to graph that. You could go through and say, well, you know, if I set x equal to 0, then I get 4 equals y squared plus z squared, and so that's going to be on the yz axis that has, you know, 1, 2, 1, 2, 1, 2, 1, 2, has those intercepts, and so we would end up with, oh, hold on, right? So what do we say? If it's not equal to, then it should be dashed. Almost made a mistake there. So we've got dashed. Oh, I'm getting better at drawing circles with this writing tablet. And so you could go through and do the same thing with y. You do y equals 0, and then you get 4 equals x squared plus z squared. All right, so then we want to go 1, 2, 1, 2, and we have a dashed line. And then finally, you could do z equals 0, and you'll get 4 equals x squared plus y squared. And so we'll have a dashed line. And the dashed line does make it a little bit harder to see the depth. Looks better with a solid line, the sphere. So we have a sphere that's just drawn with a dashed line. Okay, and then so where where is the inequality true? Is it inside the sphere or is it outside the sphere? The easiest way to check is just to plug in a test point. So if you take the origin where we've got that little arrow, plug it in, 0, 0, 0. Is 4 greater than 0 squared plus 0 squared plus 0 squared? Yes, that tells us that we want to shade inside the sphere, and you don't just do your best here. We're shading in there. So I don't want to shade too close to the dash line or it will make a mess. And that's the sketch of the domain. That's how it works. Okay. Next, we're going to move on to graphing functions, graphing these multi-input functions. Okay, so first let's start off by recalling how did we go through and graph functions with a single independent variable, right? So to graph f of x, we set y equal to f of x. We said y is going to represent the outputs, and that enabled us to create an equation containing both y and x, And then after that, we could go through and graph, and we can go through and graph that equation. We could graph the XY pairs that satisfy that equation. Right? So back when we had a single independent variable function, what we did is we started off with a function, then we took that function and we turned it into an equation by setting it equal to y, and then that gave us y and x, and then we could go through and use that combination to go through and graph the function. Right, so we're just gonna take that idea and just extend it. Right, so to graph f of x, y, what we're going to do is we're going to do the same thing, except we're going to set z equal to f of x, y. Okay, so let's go through and try some examples so we can see how that works. All right, so let's suppose that you were asked to go through and graph f of x, y equals x squared. All right, so you're given that as your function, and you're asked to go through and graph it. All right, well, what we're going to do to graph it, first thing we're going to do is we're going to set z equal to f of x, y. So, or we're going to replace with f of x, y with z. So we're going to turn this into z equals x squared. Z represents our outputs when it comes to having two independent variables, just like y represented the output when we had one independent variable. All right, so to go through and graph z equals x squared, we've done this before, right back in the quadric surfaces video. And in that video, if there is no y, then that tells us this is a cylinder. Okay, and so to go through and graph it, let's start off by drawing a coordinate axis. All right, and then once you've drawn your coordinate axis, what we want to do is we want to go through and sketch this somewhere. Now, the easiest place to sketch it is where y equals 0, right? So we want to just, that's gonna give us a nice location, and that's going to be the xz plane. So we want to take this and sketch z equals x squared on the xz plane, and then when we're done, what we do with the fact that y is missing is we take our graph and we extend it in the y direction. So anytime you have two variables, that's going to produce a cylinder, you want to start off by just going through and graphing the object that's defined by just those two cylinders, just those two variables, and the place that you put it is on the plane for those two variables. So since we have z and x, we're going to graph that on the xz plane. How do you go through and graph z equals x squared? Well, one easy way to do it is you could just kind of plot points. Right? If you plug x equals 0 in, then z equals 0 is the output. If we plug in x equals 1, then z equals 1 would be the output, right? So it'd go over 1, up 1. You plug in x equals -1, that's here. You're still going to get z equals 1 as the output. If x equals 2, then we're going to get 4. So it's at 1, 2, 3, 4. I don't know. We'll say something like that. And then -2, you'll get -4. Right? And you want to just try and go up about the same amount. The way that you can tell when you've gone up about the same amount is that these two lines, these 2 points, if you kind of drew a line through them, it would be parallel to the line that went through to the x-axis. That's how you can tell that you've done it right. Okay, and then somewhere right between the two would be where 4 is. And then once you've got your points, you just draw a curve that goes through them. Okay. And so that gives us our z equals x squared that's located on the xz plane. And again, so to finish the graph, this is not the whole graph. We need to take into account the missing y. You need to take this and extend it in the y direction. And the way that you could do that is just pick a spot here, and you just want to draw that curve again as best you can in that spot. And just try to do your best here. It doesn't have to be perfect. And then just we'll just draw some lines to denote the fact that it's kind of being extended here. And you'll notice I'm putting the lines where our points were. Right, and that gives us the surface. Sorry, the surface. That gives us the graph. Right, now the graph ends up being a surface. So that's the way that graphs of multiple input functions end up producing. So if you have the graph with a single independent variable, you get a curve, right? That's our y equals f of x. If we're going through and graphing f of xy, then we're going to end up with z equals f of xy. And if you've got three variables, x, y, and z all together, two independent, one dependent, then you end up with a surface. And so the graphs for your functions are going to be surfaces. If you end up with a surface, then you've done it right. Okay. Let's try another one. I think there's room right here on this page. So we could go through and do f of xy equals 4 minus x squared minus y squared. And so again, your first step is just to replace f of xy with z. Z is our output variable. All right, and you'll end up with something that that we have gone through and graphed things that looked like this before. This is a paraboloid. We graphed these in the quadric surfaces section as well. And you can go through and find cross sections to help you graph it. So let's do this, put this here. All right. And then once we've got our coordinate axis, then what you can do is, again, you can go through and you can just use cross sections. So you could say if x is 0, then we'll get z equals 4 minus y squared. So 4 minus y squared. If you're not sure how to, what that looks like, again, what you can do is you can just kind of use some test points, right? So if y were 0, what would you end up with? You'd end up with 4 for z. So if you just kind of go up 1, up 2, up 3, up 4, you're going to get 4. And then if y is 2, then z is going to be 0. So you could just do 1, 2, and you'll get an intercept there. And if y is -2, then we'll get 1, 2, and we'll get an intercept there. And then you can just end up with a parabola that's opening downward. Okay, and then you could do y equals 0, and we'll get z equals 4 minus x squared. And so we've got 1, 2, 1, 2. And it's the same, right? So if you plug in x is 0, you get z equals 4. And then if you plug in x equals 2 or -2, you're going to get z equals 0 at those 2 points. And then finally, you could go through and you could plug in z equals 0, right? And then you'll get 0 equals 4 minus x squared minus y squared, which is x squared plus y squared equals 4. And we've already got the 4 points there. You just need to put the circle in that connects them. And there you go. That's your sketch of the function. Oh, and I should comment on this, right? So exactly the way that graphs of functions work with a single independent variable, they work the same way with two independent variables, right? So if I went through and looked at my picture here and I just picked a point, okay, I just picked a spot on here, like how about this spot right here? So that's the spot, right? That's going to be the spot 1, 0, right? 1, 0 is our input. To find the output, you just go up to the curve, and however far you have to go up, that's going to be the output, right? So how far is that? You could kind of eyeball it. It looks like it's about 3. And if you just take f of 1, 0, what happens? You get 4 minus 1 squared minus 0 squared, and so you do get 3. Okay, so the graphs of the functions work exactly the same way as the graphs of the functions do with a single independent variable. And that is that you can use the graph to actually go through and find input-output pairs, right, by picking spots on the XY plane as your input. Okay, so just like I chose 1, 0 as my input, and then my output would be how far I went in the Z direction before I hit the curve. That's exactly the equivalent of what you do when you have a single independent, the graph of a single independent variable function. Okay, and so just want to make that clear that the graph is a visual representation of the function, and it can actually be used to go through and approximate input-output pairs. You could pick any point that's on here, and then you just want to go up or down until you hit the curve, and however far you go up or down, that's going to be your output to your function. All right, let's try one more. Let's say we want to go through and sketch f of xy equals 4 minus 2x minus y. Just as we did with the others, the way that you go through and do that is you start off by replacing f of xy with z. Okay, and then at that point you want to go through and sketch this object. And you may not be sure what the object is. You can go if you're not sure, you can go through and you can use traces. So let's say we have a coordinate axis. I'll move it over here because we're going to. Not going to get used to that. You've got to start at the bottom of the arrow. Then we want to go through and do this, and then this, and we've got our coordinate axes, I guess is maybe the right term. And then if you go through and so to figure out what this looks like, let's say we're not sure, you could go through and you could plug in x equals 0. If you do, you get z equals 4 minus y, right? So what does z equals 4 minus y look like? There's a few ways you could do this. You could recognize, hey, that's in the form of a line, and that's in the form of a line where we have a z-intercept of 4 and a -1 slope. So you could recognize that. You might not recognize that, but you could. So we just go up 1, up 2, up 3, up 4, and so we've got that's our z equals 4, our z-intercept at 4, and then we've got a -1 slope. So we want to go, down 1 over 1, and then you could draw a line that goes through those 2 points. Now you might not recognize that. So is there any other way to do it? Well, what you can do is similar to what I've done for the last couple. You could just plug in some points actually for this, right? So we're graphing this onto the YZ plane. Just ignore the x-axis, and if you go through and you plug in y is 0, that produces z equals 4. And if you plug in y equals 4, that produces z equals 0. And so you can just kind of find intercepts by just playing around with it. And that's perfectly okay if you get a little bit confused, on how to go through and sketch something. You could just try plugging some stuff in, and that might help get you started. Okay, but anyway, you do have to end up getting the line here. So whether you use the z-intercept and the -1 slope, or whether you use you plug in y equals 0, and that gets you z equals 4, and then you plug in y equals 4, and that gets you z equals 0. You've got to do one of those two. And then next we could go through and do y equals 0. If you'll do that, you'll get z equals 4 minus 2x. All right, so z equals 4 minus 2x. Again, if you plug in x equals 0, now this time we're graphing it on the xz plane, so just ignore the y, xz plane. And if you plug in x equals 0, you get z equals 4, which makes sense. This is where x equals 0 on the xz plane, and so we get the same point. And then if you plug in x equals 2, right, that would cause z to be 0. So we could just go 1, 2, and we'll have a point there. And then you could just draw the line that goes through those two. And alternatively, what you can recognize is that 4 is the z-intercept, and you've got -2 slope. So you go down 2 over 1, down 2 over 1. And finally, you could plug in z equals 0. If you plug in z equals 0, you're going to get 0 equals 4 minus 2x minus y. and you could get y by itself. So you get y equals 4 minus 2x. And so now we're graphing this on the xy plane. Some ways the xy plane can be the most confusing. When you have z involved, it's usually a little bit easier for people to recognize what to do. But this is just, think about it like you're looking down. If you looked straight down on this picture, what you'd see is our traditional, right, x and y. Forgive me, I was too lazy to go through and do the lines. But if you looked straight down, like if you were an eyeball, looking straight, I can't draw an eyeball at all. If you looked straight down on this, you would see this. Okay, and so what we want to do is we just want to use our traditional methods for graphing this, right? So we have a y-intercept of 4, right? You'd have a y-intercept of 4, and then you'd have a -2 slope. So you go down 2 over 1, down 2 over 1, and you've got your line. So you just want to do the same thing here. So this point corresponds to this point here up at y is 4, and then this point here corresponds to this point. So the points are already on there, and we just want to draw a line that goes through them. Right. And so you can recognize that if you looked straight down, you'd see your y and x axis, and then you could use your traditional method. Or you could use the method that I described for the other two and just say, all right, well, if I look at this, if x is 0, then y is 4. And if x is 2, then y would be 0. All right. And so what we end up with is this. So this picture. Okay. Now, what is that object? Well, what that object is it's parts of a plane. Okay, if you moved the x and y over, you'd end up with 2x plus y plus z equals 4. And this is in our plane equation form. But if you didn't recognize that, then you need to be able to recognize it when you actually draw this picture. This is a flat object. Okay, it's just going through these it's going to these pieces, these parts of the coordinate planes. And so if you have an object that intersects the coordinate planes on straight lines, then that is going to be a plane. Okay, and so that's the graph of that function. And just like with previous ones, if you picked some point in here and you went through and just said, okay, well, how far do I have to go up before I hit the curve? The amount that you have to go up is going to be your output. I don't know, that maybe 2-ish, something like that. I don't know. You can figure it out by actually plugging in, right? So what do you get if you plug in 1 and 1? Oh, looks like, what do we end up with? So you're going to have 4 minus 2 minus 1. Oh, that only equals 1. Oh, so that's the bad part of eyeballing it. Sometimes you're way off. All right. So it looks like it wasn't 2 there. We went a little bit too high. Anyway, so it is important to be able to recognize that the picture does provide us with a visual representation of all the input-output pairs. And so if you plug in inputs, then the output that you get should match up with the output that you actually see visually on your graph. Okay. One more. Next thing we're looking at, we have one more definition here, and that is going to be level curves or level surfaces. All right, so this is just a definition. A level curve for f of xy is the curve where f of xy equals k for a constant k. And a level surface for f of xyz is the surface where f of x, y, z equals k for constant k. So essentially the same definition. It's just one is in terms of two variables, right? The result we're going to end up with is in terms of two variables, and then the other one is in terms of three. So two variables, you graph two variables in two dimensions, so that's why it's a curve, and three variables you graph in three dimensions, so that's why it's a surface. So that's the difference between the two. All right, so what is a level curve? So, maybe I don't know if this will be apparent when we go through and do problems, but the nature of a level curve is it's a way to go through and try and visualize a three-dimensional object in two dimensions. All right, so that's actually what we're doing right now, but we're trying to go through and draw these three-dimensional objects in two dimensions by using some depth perception, in terms of our pictures. So this is not using depth perception. So what we're going to do is we're going to try and represent depth, with just a curve, just a two-dimensional picture. Now, how do you do that? So that's actually not an unknown idea. If you go through and you look at topographical maps or contour maps, what they do is they go through and they draw a two-dimensional map. Like you're looking down on a map, they draw two-dimensional. And then on the map, they put curves and they just put the height of the curve at that point. And so you could see mountains, or you can see mountains on the curve. Like you're looking straight down on a map, you can see mountains by the places where they have lines on the map where they have a large value for that line. They'll put 4,000 feet or 5,000 feet for a line, and that will represent the parts of the mountain. And so that's the idea behind a level curve. Is it's essentially just like a contour map or a topographical map. It's like you're looking straight down on a three-dimensional object, and then you're drawing curves, and you're labeling them with the height in order to go through and figure out how tall the object is. Okay, and then the level surface is the same idea, just extended to three variables. All right, so let's go through and see if we can make heads or tails of this. All right, so let's start off. Let's say we have f of x, y equals x squared plus y squared. And we're supposed to go through and graph some level curves. So how do you do that? All right, so the first thing that you're going to do is you're going to replace f of x, y with k. Okay, that's what the definition tells us to do. So we have k equals x squared plus y squared. Once you've done that, you're going to plug in some k values, because each k value you plug in is going to generate a specific level curve. All right, so we'll start off, we could plug in 0 for k. We could plug in 1 for k. And you could plug in anything you want. Okay, and so you could plug in 2 if you want, but I'm going to go ahead and jump right to 4. Why am I jumping to 4? And then 9. Well, it's because we have this is in the same form of a circle, right? And if we have a perfect square, then it makes it easier to go through and graph the circle on the other side. All right, so we've got some level curves here. So each one of these is a curve. So this is going to be a level curve. So that's 1, 2, 3, 4. We've got 4 level curves. And you go through and draw a coordinate axis. So we're graphing these in two dimensions, not 3 dimensions. You'd graph level curves in 2 dimensions. And the way that you're going to do it is we're going to go through and we're going to graph these, and we're just going to label them with the height. Okay, that's going to enable us to try and visualize a 3-dimensional object by just using 2 dimensions, because that height, that label. Okay, and so we start off, we've got the origin, we've got a big point there, and that's a height of 0. Okay, and then we want to go through and graph a circle of radius 1. Let's say here, 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 and here. And then you could draw the circle. Oh, you see, I cursed it when I said I was getting better earlier. And then the height of that is going to be 1 unit. And let's see, let's put it over here. Is that where I want to? Yeah, that's fine. That's fine. All right. And then 4 equals x squared plus y squared. So that would be a circle of radius 2. And so we want to draw another circle. Yep. Now I'm cursed. I said it was easy. Oh, not great. Anyway, so that's supposed to be a circle, and the radius there is 2. All right, and then we've got one more, x squared plus y squared equals 9, so that's 3. Radius of 3, right? Oh, hold on, I put 2. I put the radius. That's not right. That was supposed to be 4. All right, and then this is the last one. Oh, bigger is even harder. Totally cursed myself. Oh, that's terrible. Terrible. That looks like a box. Okay, hold on. We gotta try that again. Actually, let's do that one last. That's the hardest one. Jeez. All right, that's not too terrible. All right, and then the hardest one. Let's see if we can manage this. Oh, good grief. Maybe if you start here, is that easier? Yep. All right, anyway, good enough. All right, and then so the height for that one is 9. All right, and so the idea is that you could go through and you could look at this picture and you could see, your brain would recognize that there is a 3-dimensional object here, because this is at a height of 0, this is at a height of 1, this is a height of 4, this is a height of 9, and so that you could recognize that you have an object that is increasing as you move away from the origin. And not only that, but it's increasing faster and faster. So it's getting steeper as you move away from the origin, right? Because there's 1 change in height from here to here. There's 3 change in height to get from 1 to 4, and then there's a 5 change in height to get to here, from here to here. And so the object is getting steeper, faster and faster. So the idea is that you could look at this and you would be able to recognize that what you have is you have the following object. Oh, geez. Cursed. So the idea behind graphing level curves is that this picture, that you could wrap your mind around it, and you could imagine that you could imagine this picture by looking at this one. And again, so we've got at the origin, you've got a height of 0, and then if you go out 1 unit, right, you get this circle here, which is at a height of 1 unit, and then if you go further out here, you get another circle, which is at a height of 4 units, and then this last one here is at a height of 9 units. Okay, and so the circles that I've drawn on here, they match exactly with the circles that are drawn on this picture. This top circle is that one. This circle is that one. This circle is that one. And then the origin, the little dot there, is that little dot there. All right, so the idea when you go through and graph level curves is it enables you to graph an object that is a 3-dimensional object purely in 2 dimensions without trying to do any kind of depth perception, or any of that. And the way that you handle the depth is by going through and just marking on a map the height of the curve that you draw, right? And that's the same idea that they do with topographical maps, which are highly useful. And many people who go out hiking use them to determine their path. Okay, so that's the idea. All right, let's do one more level curve. So we get f of xy equals x plus y. And then we want to draw some level curves. So we're going to do k. First, you want to do k equals x plus y. Then we want to just plug in some stuff for k. So you could plug in 0, like we did last time. There's no reason to go through and plug in anything special this time. You could just plug in 1. You could plug in 2. You could plug in a negative value, or there's nothing to stop you from doing a negative value. Why did I not do negative values last time? Well, if you look at it, it's because negative values didn't make sense. We can't have a negative value equal to a sum of squares. That's why I didn't use negatives last time. Once you've got your equations for your level curve, you go through and draw your coordinate axis. And then we just want to go through and draw those curves. So how do you draw these curves? Well, you could translate this into traditional format for these are those lines. So we could just translate this into y equals negative x. This translates into y equals negative x plus 1. Here we've got y equals negative x plus 2. And here we've got y equals negative x minus 1. And so y equals negative x, that's going to be the line that goes to the origin that has a negative 1 slope. So that would be this line. And once you've graphed the line, you want to label it. So what is the height at y equals negative x? The height is 0. And then we want to go through and graph y equals negative x plus 1. So that's the line with a negative 1 slope and has a y-intercept of 1. We'll say that's 1 unit there. And so we're going to get the line parallel to the one we just drew, like that. And the height there is 1. And so if we're trying to visualize in 3 dimensions what's happening here, we've got a consistent, right? A consistent increasing slope, right? So if you were moving this way or this way or this way, right, you'd be climbing upward as you went from a height of 0 to a height of 1. And that continues like with the next line, right, where we've got y equals negative x plus 2 that has a y-intercept of 2 and a negative 1 slope. So you're going to get another line again that's parallel to the previous 2. And so if we were to walk up this way or here, we would be walking up the same slope, right? The same steepness. Okay. And then if we do one more that has a negative 1 slope, and so we would get that. And so we've got, if we label that, that's negative 1, that's 2. And so this is at a height of negative 1, height of 0, height of 1, height of 2. So we'd be going upward as we walked from negative 1 to 2. And it's the same path essentially in terms of how steep it would be if we walked over any of these different pieces. And so that's just ways you could look at the picture and gain some degree of interpretation. What is the object? What type of object do we have that's flat like this? In terms of, by flat, I mean that it's consistent in terms of the way that the pattern looks, here versus here versus here. That's a plane, all right? So planes are like, you took a piece of paper and you just held it up. If you were to move up the piece of paper, from one side to the other in various different places, you'd have the same steepness depending upon how you held the paper. A little hard to represent that and, without being able to show you a picture, but you have to use your imagination. Okay, and then let's do one more, just in case. So level surface. It's a level surface. So it's the same idea, just extended to 3 dimensions, right? So we want to go through and graph some level surfaces. So we have f of x, y, and z equal to x squared plus y squared plus z squared. And the way that you want to start off with a level surface is you want to replace f of x, y, z with k. Once you've replaced it with k, then you want to plug in some k values. So you could plug in 0. You could plug in 1. And then you could plug in, let's say 4. You could plug in 4. Why 4? Because this is in the form of a sphere, and we have the radius, and the radius is squared on this side. Okay. Once we've got that, we can draw a picture. Let's make the picture really big here. It'll make it easier to graph. All right. And so we have 0. That's our first level surface. And then x squared plus y squared plus z squared equals 1. That's going to be a sphere of radius 1. So let's say this is radius 1 here, 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 and here. And so we've got that. All right. And so when you go through and graph your level surface, you do still want to label these, right? So this is 0. That's going to be our output of 0. This is 1. This surface represents our output of 1. And then the last one we're going to do is 2. So if that's 1 unit, then this would be another 1 unit. Another 1 unit. There. 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 And there. And let's see if we can do this. Yeesh. Counterintuitively, it's easier to draw smaller objects. All right, let's try that last one more time. I give up. All right, that's not bad. That looks like a sphere. It came out good. All right, and then the output for that is 2. All right, so you might be wondering, how do you interpret this, right? So in our previous picture, we interpreted this as heights, right? So this line is a height of 0, this line is a height of 1, this line is a height of 2, and so you can easily imagine, okay, if I went in this direction, I'd be going upward, right? And so I'd be climbing, 1, 2 units upward as I moved along this line. And so you've got heights. The outputs represent heights. So what do the outputs represent in, with a 3 independent variable function? Well, you need to pick an application, right? So usually the one that I use is temperature. I think it's the easiest to imagine, right? So what you want to pick is you want to pick something that you would have at every point in 3 dimensions. And I think temperature is kind of the simplest example to start with. And so if we apply temperature to this, here the temperature is 0. And then as we move outward from the origin in any of these given directions, the temperature rises 1 unit. And so we've got a 1 unit increase in temperature as we went in, well, any direction, but in this direction. And then as we went you have another 1 unit increase. And if we did another line, another surface, we would have, whoops, that's not supposed to be 2. That's supposed to be 4. I made the same mistake twice. Whoops, sorry. And then so this should be 3. That makes more sense, because this should be the 3-dimensional version of the picture that we did earlier right here. It's the 3-dimensional version of this. And so you have a 1 unit increase in temperature as you move from the center out a distance that's in a sphere of radius 1. And then you've got a 3 unit as you move even further out from the center. And so for whatever reason, the temperature is very, very small here at the center. Maybe you've got, I don't know, it's in a room and there's a snowball that's there, and the snowball is going to cool the temperature in the region where the snowball is. And as you move further away from the snowball, the influence of the cold object decreases. So anyway, that's one way to go through and try and wrap your mind around what a level surface could represent, would be temperature. Okay, so that concludes the video. Thank you for watching. I'll see you next time.